All right, let's talk about the speed of sound. Now, I know what you're thinking. It's something we all learn about in school. But what if I told you that this basic concept, something we experience every day, is actually a key to unlocking the secrets of the most bizarre and extreme places in the entire universe? Well, today we're going to go on a journey from a backyard fireworks show all the way to the dead heart of a star. You know the scene, right? Looking up at the night sky, waiting for the next big firework to go off. It's beautiful, it's loud, and it's also a perfect little physics experiment hiding in plain sight. I mean, it's a question we've all probably asked as kids. You see that brilliant explosion of color light up the sky, and then you wait. A second, maybe two, and then, boom, the sound finally catches up. And you know what? That little delay, that's not just a quirk. It's a fundamental clue about how our universe is put together. And this lag, this gap between seeing something and hearing it, it happens all the time. Fireworks, a lightning strike, and the thunder that follows, really anything far away that makes a noise. So let's get into exactly why that is.
Okay, so the core reason is pretty straightforward. Light is the undisputed speed champion of the cosmos. It's just ridiculously fast. Sound, on the other hand, kind of plods along in comparison. But here's where it gets really interesting. See, the speed of light is a constant, a universal speed limit. The speed of sound? Oh, that's a whole different story. It's flexible.
Right. So this is the key thing to wrap your head around. The speed of sound isn't one single number. It changes its speed based on what it's traveling through. It's a total chameleon. You see, sound is just a vibration, right? It needs something to travel through, some stuff to pass that vibration along from one particle to the next. We call that stuff its medium. That could be air, water, even the ground beneath your feet. It's also why there's no sound in the vacuum of space. There's simply nothing there for the vibrations to vibrate. So what determines the speed? Well, you can think of it like a constant tug of war between two big properties. First, you've got rigidity. That's how stiff a material is. The stiffer it is, the faster the particles snap back and pass the vibration on. That wants to speed sound up. But then you have density, how much stuff is packed into a space. More stuff means more inertia, more mass to get moving, and that wants to slow sound down. And just look at how dramatic this tug of war can be. In air, sound moves at about 331 meters per second. Not bad. But then look what happens when it hits water. It's suddenly going over 4 times faster. And then look at a solid, like steel. The speed just skyrockets to almost 6,000 meters per second. That's because the atoms in steel are both incredibly rigid and packed super tight, letting that vibration zip through almost instantly. You know, some animals have totally mastered this. A bat sends out a tiny squeak, and by timing how long it takes for the echo to come back through the air, it can build a perfect 3D map of its surroundings, all in complete darkness. It's incredible. So if there's one rule to remember for our everyday world, it's this. The stiffer and less squishy something is, the faster sound is going to travel through it. Now, I want you to hold on to that rule because we're about to take it somewhere, well, somewhere that's about as rigid and dense as you can possibly imagine. Okay, we are officially leaving Earth behind. We're going to one of the most extreme objects in the known universe, a neutron star. This is what's left over when a giant star dies. It's so dense that a single teaspoon of it would weigh billions of tons here on Earth. Just try to picture that. Now, based on our rule, right? More rigidity, more density, that should mean a truly mind-bendingly fast speed of sound. But what happens when the stuff sound is traveling through isn't even made of atoms anymore? What happens when it's something way more fundamental? I mean, just look at this comparison. On one side, you've got sound bumping between molecules in the air. But inside a neutron star, the pressure is so insane that atoms are literally crushed out of existence, leaving behind this soup of fundamental particles called quarks. The normal physics playbook gets thrown out the window. Down here, everything is governed by quantum chromodynamics, the physics of the strong nuclear force itself. So, for a long time, physicists have been trying to figure out how sound behaves in this bizarre quark soup. They even had a theory, a kind of cosmic speed limit for sound. But, as it turns out, neutron stars had a pretty big surprise in store for them. The theory went like this. No matter how dense or weird the matter got, the speed of sound should never, ever exceed about 57% of the speed of light. It was supposed to be this absolute unbreakable ceiling. An incredibly fast ceiling for sure, but a ceiling nonetheless. So what happened? Well, it all comes down to a really bizarre quantum effect with a wild name, a color superconducting gap. Now, don't worry about the name. All you need to know is what it does. Think of it like a switch that flips on at these insane densities. Quarks start pairing up in a special way, and when they do, it makes the quark soup dramatically stiffer. And what did we learn earlier? More stiffness equals faster sound. So check out what the research actually found. It's fascinating. At the absolute highest densities deep in the core, the speed of sound acts like they thought. It gets really close to that cosmic speed limit. But then, as the density decreases a little, the speed of sound takes a dip, and then, because of that weird superconducting gap, it shoots up like a rocket, peaking above the speed limit they thought was impossible to break. And here it is. This is the punchline. The old limit was expected to be around 57% the speed of light. But what we're now seeing is that the actual maximum speed of sound inside a neutron star can blow right past that. Sound is literally breaking its own speed limit. Okay, so why is this a big deal? Is it just some weird cosmic factoid? No, not at all. This discovery gives scientists a brand new and totally amazing tool to peer inside an object that is fundamentally impossible to see directly. Think about it. We can't send a probe into a neutron star. We can't put a thermometer in there, but we can listen to it in a way. And by measuring how fast sound travels through its core, we can figure out exactly what kind of exotic physics is happening deep inside. The researchers who figured this out put it perfectly. They said that by using observations to constrain the speed of sound, they can actually estimate the properties of that crazy quark matter, like the size of that all-important color superconducting gap. And this is how they do it. When two neutron stars collide, they send out gravitational waves, literal ripples in the fabric of space-time. Our detectors, like LIGO, can pick up those faint ripples. By analyzing them, scientists can figure out how squishy or stiff the stars were during the collision, which tells them the speed of sound inside. And that speed of sound, that's the final clue that unlocks the secrets of the quark soup. It's just an incredible piece of cosmic detective work. And that leaves us with this really amazing thought. We started with the simple delay between the flash and the bang of a firework, and it led us all the way to a brand new way to explore the fundamental nature of matter itself. It just makes you wonder what other secrets are hidden in the cosmos, just waiting for us to figure out the right way to listen.